There are several different ways that interfaces can help people think more fluidly by distributing the cognition into artifacts in the world. When interfaces help people distribute a cognition, it can encourage experimentation, it can scaffold learning and reduce errors through redundancy, it can show only the differences that matter, it can convert slow calculation into fast perception, it can support chunking, especially by experts. It can increase efficiency of interactions, and it can facilitate collaboration. Let's go through these one at a time. Here's a video game that I bet many of you all know. This is the Tetris video game. And there was a very clever study that David Kirsch and Paul Maglio at UC San Diego ran, where they looked at Tetris players playing Tetris. And what they found was really interesting. In Tetris, as you may know, you can use keys to move objects around on the screen. And at a certain point, you can hit the space bar to drop the object and try and get a row of filled blocks. Moving and rotating pieces on the screen may seem like a waste of time because you have a limited amount of time before the block hits the bottom. So, how do you use that most efficiently? It turns out that people move the block around the screen more than they, in some purely theoretical sense, need to. So, in essence, I'm trying out different places that the blocks could go. Maybe this is just for novices, that when you're learning Tetris, you need to feel things out, but as you become more of an expert, that's no longer the case. Exactly the opposite. Kirsch and Maglio found that experts actually relied more heavily on moving objects in the world. And what they were doing is they were distributing the cognitive effort of what-if scenarios. What if I place it over here? What if I place it over there? You absolutely can do that in your mind. But it turns out that in this case, for most people, it's cheaper to do it out in the world, to be able to turn the cognitive task of reasoning about all of the what-if scenarios into a perceptual task of, oh yeah, that block would work perfectly right there. It saves you the effort of having to, in particular, mentally rotate the different pieces to figure out how they would fit into the screen. Here's another example from the learning sciences. These are called Montessori blocks. And what we have here are beads that provide a physical representation for number, especially for young children. Numbers are a really abstract concept, difficult to get your head around. And these physical instantiations can help teach addition and multiplication and other simple arithmetic operations. So for example, if I wanted to take 3 and multiply it by 3 to get 3 squared, well, I can see here that I have 3 by 3, I have a square, and I can see that it's composed of 9 beads. And there are other addition and multiplication options that you can do with these also. And by having this redundant information, by taking an abstract concept and reifying it and making it concrete, it can help scaffold learning and reduce errors. The Montessori blocks example and the Tetris example show us the power of providing a visual or physical instantiation of abstract ideas. So what makes a good representation of this sort? Well, you should show the information that you need and nothing else. And what these representations should do is it should enable the kinds of tasks that users want to do, like comparison and exploration and problem solving. And if that seems too abstract or maybe obvious, let's take a look at this example from the London Underground. This subway map was introduced about a century ago, and it was one of the very first maps to introduce a brand new idea in map design of abstracting the layout of the tracks from the underlying physical geography. Prior to this London subway map, the maps would show what the geography was, and so long things were long and short things were short, and if the tracks wandered because that's the way that it worked, then the tracks on the map would wander because that's the way that things worked. And what the underground map designers realized was that the most common task for subway riders is to figure out how to get from point A to point B. And all of this additional detail of faithfulness to the underlying topology was getting in the way of that A to B task more than it was helping it. And so what they did is they stripped out a lot of that unnecessary detail, turning this into vertical, diagonal, and horizontal lines. So there's some representation between the layout on the map and the layout in the real world. North is north and south is south, and things roughly head in the direction that they do in the real world, but the detail is stripped out. And this makes it much easier to be able to figure out how to get between connections. Another thing that they did is they introduced what a century later we would call a focus plus context representation for the map. In the center of London, the subway stations are very densely packed, so that area is expanded out. It consumes more of the map real estate. As you get out towards the suburbs, the stations are fewer and further between. As opposed to that taking up 90% of the map because it's 90% of the space, those stations are actually squinched. Because if you know you need to go northeast to a particular station, then the exact distances involved are most of the time less relevant. Now, of course, what constitutes a good representation is, of course, task specific. And so what you can see is that by making some tasks easier, like getting from A to B when you know A and B, or being able to navigate the center of London more effectively, you've compromised on other tasks. And so for somebody who may need to make decisions about what stop to get off at based on some underlying topography, or another task that's compromised is by virtue of the distance between the stations on the map not lining up between the distances between stations in the world, you can make poor judgments about what's close and what's far. In the center, you may believe things are far apart when they're really close, and out in the suburbs, you may believe from the map that things are closer than they actually are. And so nearly all representation design is about fitness to task. Here's a temperature map from the Weather Underground. It shows the temperature at each location in the Bay Area geo-referenced so that the temperature number is placed right on top of that physical location. What do you think of the benefits and drawbacks of this representation? What's it good for, and what's it a problem for? If you know the physical coordinate that you'd like the temperature for, say, for example, what temperature is it along the coast, and I don't care or don't know the exact name of the town, this works incredibly well. It's also a reasonable interface in some sense for trying to get a gestalt of what are the temperatures like in the area overall. I can see, for example, as I head inland, the temperature tends to get warmer. There are a lot of ways in which we could make this better. So right now, every temperature is shown identically, no matter what temperature it is, which means it's hard to scan. I have to read every single temperature one by one. I could make this better if instead I had the temperature number somehow the color or size of the temperature number correspond to the weather. But if we're going to start mapping the variables of a map to something like color, we need to be careful to get it right. This is an example that comes from Edward Tufte. His books on visual design and the graphical representations of data are fantastic, and I strongly encourage you to read them. In this map, we see how a computer scientist might make a mapping for Japan. This is showing the height above or below sea level as color. And what you can see is that the depth below sea level is represented by the color spectrum, Roy G. Biv. Now, one of the challenges of hue is that it's not an additive representation. So there's not really a strong ordering that we give to the colors perceptually. It's a substitutive representation that red and yellow are qualitatively different, but we don't automatically have a more than, less than relationship between the two. Another problem with this representation is it's very difficult by glance to tell what's higher and what's lower in the sea. Conversely, the individual isosurfaces, the individual chunks of a particular depth really pop out. Like, to me, for example, the yellow depth pops out very strongly, and that shape really comes to the attentional fore, which, if you were making a rock and roll poster for the Fillmore, would be awesome. But if you're trying to get a sense of the contours of the sea, what becomes salient to you, the outlines of what's 400 meters below sea level, it's probably just not that relevant. So how could we continue our theme of using color as a representational cue, but have it be more meaningful than you might see in this case where we're mapping it to the color spectrum? And here's Edward Tufte's redesign, which I think is much better. There's a couple of things that I really like about the representation here. The first one is that all of the things that are above sea level are brown, are kind of an earth tone. So we're leveraging our intuitions about the physical world and using that metaphorically for the map. So the land-colored stuff is land. Similarly, all of the water is blue. The water-colored stuff is water. And furthermore, we can see how the intensity or the luminance of that color blue changes with depth. And the deeper blues are darker blue, which corresponds to our physical intuitions. And of course, water doesn't really get that much darker at the kind of depth that we're talking about here. Our intuition about darker colors being deeper comes from much shallower depths. But the idea, you can leverage this thing that we all know, that water right by the shore is a paler color, and as you get more of it, it gets darker. So this is a really wonderful way to see that these darker areas here are deeper than these shallower areas here. With the London Underground map, we saw how the representation of the map, what makes a good representation, was intrinsically tied up with the task that the user was doing. Similarly, what makes a good representation is also dependent on what a user's expertise is. And a wonderful example of this comes from Herb Simon and David Chase in the early 1970s. They were looking at chess as an exemplar domain for trying to understand expertise. One of the things that they observed was that expert chess players were much better at being able to remember the configuration of a chessboard. You can imagine a couple of hypotheses for this. So one of them would be experts were born with a better memory for that kind of thing. Or similarly, experts, by virtue of their 10,000 hours of training, have trained themselves up to build up that muscle and be really good at remembering that kind of thing. Neither turns out to be the case. Experts are much better at remembering the configuration of a board, but only if it's an actual game. So if the configuration of the chessboard is the configuration that a chessboard could be, experts do a fantastic job of remembering it. But if you arrange the pieces on the board in a way that chess play could not ever achieve, the experts actually do no better than novices at all. And so what we're seeing is that the ability of experts to chunk things and have higher memory capacity is because they're able to leverage their knowledge about the domain. Game design and user interface design are both concerned with how easy or hard is it for a user to accomplish a particular task. The difference is that often game designers want to make it hard, the right hard, and interface designers often want to make things easy. And so we can learn from this chess example, and we can ask the question as interface designers, can we make interfaces more chunkable? Can we make interactions that can be accomplished in one chunk and therefore place a lower load on our memory and make it easier for users to work with? A great example of this comes from Bill Buxton, who looked at being able to move text between locations on a document. And in a common desktop user interface today, one common operation would be either a keyboard shortcut or a menu command to cut some text, and then you move the cursor to the new location and you paste that text. That's 3 different operations, and in between, if you got interrupted, you might forget what's in the copy buffer. In fact, I'm sure that's happened to all of us at some point. What Bucks then realized is, well, what if you could turn all of this through a gestural user interface into one command? So maybe I could grab the text that I want, draw a new location, and drop it right there. That'd be much better. There's never a time where I could be interrupted and lose state because all of the state is maintained in this continuous gesture. We've all heard the saying that a picture is worth 10,000 words. As interface designers, we're tasked with the project of representing the information to the user. And one task that we commonly have to deal with is, should we represent information visually or should we represent information textually? The answer, of course, is it depends. But one time when representing information visually can be much more effective is when you can convert slow reasoning tasks into fast perception tasks by virtue of making them visually salient. We saw that with the map example. In that case, both the colorings of the map were visual, but one, it was much easier to just at a glance understand what's going on in the good coloring, and in the poor coloring you had to reason about it much more slowly and the wrong things kept popping out. If you think about a table of numbers, it can often be difficult to see trends, whereas if you represent that same information visually, it can often pop out what the high points, the low points, trends, outliers, all of that becomes salient and automatically visible to you.